Hello everyone, welcome to Rasayan Academy, all of you. So guys, this is another video of name reactions, and in this video we are going to consider three important and very similar name reactions which are causing a lot of confusions to all of these students, right? And these are very similar reactions, and that is why we need to understand the little difference that they have and what are they used for, right? So the three reactions are the Appel reaction, right, or I would rather call it the Appel reaction. Okay, then there is the Mitsunobu reaction, which is very similar, doing the same job as the Appel reaction, and the corey-fuchs reaction, which will have the same reagent combination as the Appel reaction. Okay, so these reactions are super important. Let's talk about them one by one. And also in this video I'm only discussing these three name reactions. What you have to do is just go through the previous year questions of CSI and Net and Gate. You will find a lot of similar questions, and I will also do a video on this later on. Okay, so for now, just understand the reaction and the mechanism. We will do the PYQs after this is done. Okay. All right, so first name reaction, and this has become our 59th name reaction. All right, very well. So the first reaction today is Appel reaction. Now, what is it, guys? A very simple reaction, as you can see. Looks like that this is an SN2, simple SN2 mechanism, isn't it? The substitution of OH and causing inversion to introduce a halide. Although this reaction is very easily possible by just providing a OH minus. The reverse reaction is difficult because OH is not a good leaving group. So what we have to do is we have to apply some special case, some specific reagents to make this OH a good leaving group and then make it leave, right? So that is why we have the phosphine over here, because of the oxygen phosphorus very strong bond forming tendency. It's going to extract away the oxygen and hence making it a good leaving group. Okay, so yes, the Appel reaction is the reaction of triphenylphosphine and tetrahalomethanes. Okay, so triphenylphosphine PPH3 or trialkyl, any other alkyl group can also be taken. Tetrahalomethanes CX4, all the halogens. Usually CCl4 and CBr4 is used, okay, because of their polarity, bond polarity. We need the bond polarity. Why do we need that? You will see that in the mechanism. Okay, so usually tetrahalomethanes CCl4 CBr4 are taken, and this is taken with the alcohols to convert an alcohol to the corresponding alkyl halide, okay, under mild conditions, so that the other groups, other sensitive groups are not destroyed. So let's quickly see what is this reaction. We have an alcohol, we have CX4 and PPH3. Now this combination is super important, and this is going to lead to this reaction formation. Let's quickly see the mechanism first of all. So here we have a triphenylphosphine and you have a tetrabromomethane molecule. Let's write it like this simple way. Now the phosphine is supposed to attack on one of the bromines. The bond falls up like this on the carbon itself. Phosphorus gets a positive charged like this, okay, and we have CBr3 minus, which is free. Okay, so what is this CBr3 minus going to do? The CBr3 minus, since there is an acidic proton in the medium, what is the acidic proton? Pay attention, this is the super important step. Let's say I have a chiral carbon having all the different groups. Here you have a acidic proton, that's why it is abstracting this acidic proton. Okay, if you don't have this acidic proton, a different mechanism will follow that we are going to use in the corey-fuchs reaction. Okay, so first of all you have this acidic proton which is connected to oxygen. It is going to abstract it, and you get O minus over here, R dash, H, CBr3. Bromoform is separated. Very well. Now along with that you also have this positive phosphonium ion over here. So the O minus, because it has a huge affinity for phosphorus, can be attacked like this, and the bromide got removed. So ultimately you are getting this intermediate oxygen connected to phosphorus triphenyl phosphorus group like this, R dash, and it is still above the plane. Okay, so there is no change on this carbon center as of now, so don't do this mistake of writing this below the plane. Okay, yes. Now there is a Br minus which was free. What are we going to do with the free Br minus? So simple. The free Br minus is going to attack from the back side, and it's going to give you a simple SN2 reaction to lead to your product like this. This is your product, and along with that the byproduct is your triphenyl phosphine oxide. So this is the driving force of this reaction because of the strong oxygen phosphorus bonds. This is your driving force of this whole reaction. Okay, yes. Now it is not a very difficult mechanism. The phosphine attacks the bromine. Why is the phosphine attacking the bromine? Why not the carbon? Because carbon is hindered, it cannot undergo an SN2 reaction, and also because a CBr bond is polarizable. It is polarizable. So in the previous slide you have just seen that we usually take either CCl or CBr bond. Why is that so? Because we need the phosphine to attack over Br and the Br to shift its electron density to carbon. If it was CF4, it would not have been possible. Okay, so that is why we are having the bromine over here easily polarized. All right, so this is how the mechanism goes for the Appel reaction. Just a simple SN2 reaction. Only extra stuff that is present over here is conversion of the OH into a good leaving group, just like this one. Okay, yes, very well. So keep this step in mind. I have told you that you have a acidic proton over here, so it is grabbing the proton and leaving as bromo form. Let's see what is next. Next is your 60th name reaction, Mitsunobu reaction. Why do we have this reaction over here? Because as you can see, you have a similar reaction. You have taken the chiral alcohol, the exact same alcohol that we have taken in the previous slide. Okay, so the exact same alcohol, and over here you see you are having a protonated nucleophile, HNU. That means a protonated nucleophile in the presence of a dead molecule. What is that? Diethyl diazo dicarboxylate. Diethyl diazo dicarboxylate. This is your dead molecule. Alright, sounds very deadly. So handle with care. And what does it do? It just gives you a simple SN2 reaction. Alright, and along with that, it gives you the same phosphine oxide, which is again the driving force of this whole reaction. And the dead molecule, the double bond has opened up. It is now protonated on both the nitrogens. So very similar mechanism to Appel reaction. Here you are using triphenyl phosphine PPH3 along with the dead molecule. Okay, yeah, this must be written over here. All right, now let's see the mechanism. It's not very complicated, right? So what do you have? First of all, over here you had the phosphine and you have the dead molecule, right? So what is this combination going to give you? Let's just write it down over here. This is your dead molecule. All right, now phosphine, you will see again working as a base. Now these nitrogens are, close to the carbonyl, so I would not say that these two nitrogens are very electron rich. I would rather say they are electron deficient, and one of them would very easily be attacked by the lone pair of phosphorus. What happens next? Next is you had a protonated nucleophile. Yes or no? This is your protonated nucleophile over here. So the protonated nucleophile, the proton is going to be abstracted and nucleophile comes away like this. So you have one NH bond formed, one NPPH3 bond formed. Phosphorus got a positive charge, rest of the molecule as it is. rest of the molecule as it is. Okay, now what next? Now as you can see, you have got a positive phosphorus. You would imagine that we also have a alcohol in the molecule. And guys, pay attention, this whole reaction is a one pot synthesis, or let's say one pot reaction. What is that? Everything, all the reagents just added everything together, no step by step addition, everything is added together. So you have the alcohol in the molecule right now, and which is going to, yes, the OH is going to attack the phosphorus over here, and you get a negative charge on the nitrogen. The bond has fallen over nitrogen, CO2 ET once again, and you have the R O H PPH3, positive charge on oxygen, and this is R dash. Okay, this is R dash, chiral carbon. So the negative charge is going to obviously take away the proton, and you are going to get this alcohol, alcoholic OH group, now connected to PPH3. Okay, so what is your role now? In the overall reaction mechanism that we did till now, your alcoholic group, OH group, was made a good leaving group like this, and your nucleophile is also free. You have a free nucleophile just in the first step. So what is the free nucleophile going to do? It is just going to do another SN2 reaction. And sorry, yes, this SN2 reaction would lead to your product like this. The nucleophile is added. Along with that, you get the phosphine oxide, O double bond PPH3. Along with that, you have this protonated dead molecule that you had written. Okay, so this is what you have. NH, CO2, ET. Now, what is this nucleophile? Is there any specific criteria for this nucleophile to be? Yes, there is one. Because, see, what we are doing is we are deprotonating the nucleophile in the first step. So, we are not supposed to take like a very poor acid compound. Our nucleophile could be, and most frequently, the nucleophile used is some organic nucleophile, let's say benzoic acid. Okay, and if it is para-nitrobenzoic acid, it will be even better because the proton will be lost even more easily. Okay, so final step, guys, you are actually having one something even better than adding in halogen, because you are adding such a group so that you can hydrolyze this group, and you can get even more benefits of adding this group. Okay, if you are adding this OH oxygen over here, if it is at like this, if the oxygen attaches over here, you can get different functional groups from it. Okay, so the nucleophile is not necessarily a halogen. It could be a halogen, it could be acetic acid also, it could be benzoic acid also. So you are getting this particular name reaction a lot in your previous year questions. Okay, all right, very simple reaction, Mitsunobu reaction. So what is the similarity between the Appel reaction and the Mitsunobu reaction? SN2 reaction, substitution of the OH and replacing it by a nucleophile, causing inversion. Okay, so these two things are same in the Appel and the Mitsunobu reaction. All right, now there is one example, a very simple example as you see over here. Now this is a group which is protected, the diol is protected by acetone. Yes or no? This is a 1,2 diol protected by the acetone over here, and you have a OH group, free OH group, which is below the plane. Now, as you can see, you have para-nitrobenzoic acid. This is your acid molecule over here in the presence of dead and PPH3. What is going to form? First of all, you are going to deprotonate your nucleophile. O minus, it's going to become NO2. And in the second step, what will happen? OPPH3 will form, right? and it is going to attack over here, and this is going to leave. The whole group is going to leave, becoming the phosphine oxide, right? And then this is your final compound. Okay, this is your final compound. Now, one more utility of this Mitsunobu reaction is it's not necessary that you have the same nucleophile clinging to it as the product. You may even hydrolyze this. Okay, you may even hydrolyze this in let's say neutral conditions, so that this acetyl group is not disturbed, mild under mild conditions, and you have a inverted OH group. So this is one of the applications. This is not included in the Mitsunobu reaction. The later part, Mitsunobu reaction, is still here only. But this is the application part. Okay, this is how you can get another OH. So what did happen, guys? You started from the OH below, you got the OH above. Okay, yes. 61st 61st name reaction is your corey-fuchs reaction, and it's a very important one and very similar to Appel reaction. How? And you are getting this reaction a lot in your previous year question. Ye dekho. Now it's a very simple one. One carbon homologation, that is your step up reaction of an aldehyde to a dibromo olefin, which is then treated by N-butyl lithium to produce a terminal alkyne. Okay, let's see what is happening. You are just adding one more carbon over here in the reaction. So what is similar with the Appel reaction and corey-fuchs reaction? This part. Okay, and many a times you get both of these reaction confused. Don't do that. So it's a different one. You are using an aldehyde. You are then converting the aldehyde into something like this, which usually looks like a Wittig reaction, because in the Wittig reaction, somehow if you generate this kind of a ylide, it's going to be nothing but a Wittig reaction over here, which will further react with butyl lithium to give you this alkyne. It could also be alkyne, it could also be some other group like this. So in the place of this hydrogen, you can also add some other electrophile. All right. So let's see the mechanism of this reaction, the corey-fuchs reaction. Now, first of all, guys, we have the same combination PPH3. You have tetra bromo methane. What is it going to do? Once again, going to attack over a bromine, going to form this bond, positive charge, CBr3 minus. So I told you to pay attention in the Appel reaction that you had a you had an acidic proton over there, right, of the OH group. Here you don't have a OH group, you have a aldehyde. No acidic proton is present, so the CBr minus is going to attack back on the phosphine, releasing the Br over here. What happens next is like this. You have a CBr3, still the phosphorus having a positive charge, and one of the Br minus got free. Now the Br minus is going to attack at another bromine group and thereby giving you this kind of a ylide. Now, all of these strange reactions are possible just because you are having a CBr bond. This is a highly polarizable bond, and that's why the electron density can jump back to carbon. Okay, back and forth in carbon and bromine. That is only possible when you are having this polarizable bond. Okay, will not be possible in the CF and very less in CCl as well. Okay, CBr is very good for that. So guys, as you see, this is your ylide which we have generated. Ylide can also be written in this way: PH3P double bond CBr2. Okay, and once you get this, you know that it's going to undergo the Wittig reaction, that is your betaine formation. CBr2, PPH3 goes like this. Betaine intermediate, elimination goes like this. Alright, and along with that, you have the phosphine oxide eliminating. Once again, the driving force. Alright, so all these three reactions have the same phosphine oxide, which is running this reaction, right? Now, what about this one? So this molecule is further reacted with a strong base like butyl lithium. So what is the butyl lithium going to do? First of all, butyl lithium is going to remove this proton from here and cause elimination, giving you, I would not say it is a proper E2 elimination, but yes, very similar. It's going to give you this kind of a terminal alkynyl bromide. Now next is one more mole. You are using butyl lithium in excess or at least 2 moles, because one more mole is going to cause a halogen exchange reaction. It's going to attract the bromines. BuBr is your elimination product, and hence you have generated this kind of a anion, alkynyl anion over here. Now this anion, if we are doing aqueous workup, it's going to give you this simple alkyne. If you are adding in the first step CO2 and in the second step aqueous workup, you are going to get the acid. It is that simple. Okay, so this is your corey-fuchs reaction. Very simple reaction. This part, the reagent part, is the same as Appel reaction. However, in the lack of a acidic proton like alcohol, you are going to get the ylide formation, and hence it is going to give you this kind of a alkene dibromo gem dihalide, which on further reaction in the presence of a butyl lithium base, right? This is your product. Okay. One example of the corey-Fuchs reaction goes like this. Substituted ferrocene, you see, in the first step, CBr4, PPH3, zinc, all the same reagents. What are you going to form? You are going to form something like this. One hydrogen over here as it is, two Br bonds, and after that, butyl lithium. And see, when it is mentioned butyl lithium and nothing else, you are just going to put a hydrogen at the end. If no separate electrophile is mentioned, just assume that you're always going to have the aqueous workup. Okay, so yeah, this is going to be a triple bond like this. This is your final product of this example. Okay. Now in the following video, we are also going to solve some really important PYQs on name reactions. Stay tuned for that. And if you haven't already studied a lot of name reactions, please do. We are on our 61st name reaction. Many more important name reactions to come, guys. And yeah, I'll be coming up with more such videos. If you haven't already subscribed to the channel, please do. Please watch all the classes. Thank you so much for watching. I'll see you very soon.